All right, so we are now on page number 98 of our notes. And let me get my pen also here. All right, so this is page number 98. In our last set of notes, we worked on identifying which types of reactions are redox, like single replacement and combustions, which ones are never redox, like a double replacement or neutralization, and how to assign oxidation numbers. So today we're going to put those together, and in this video, we're going to talk about picking the redox reaction, and we're going to have to start by assigning oxidation numbers to all of the atoms in the reaction. And then if any element has undergone a change in oxidation state, we can say that oxidation reduction or redox has occurred. And then if any free elements have joined in a compound, or compounds have been broken up into free elements, redox has definitely occurred, right? So that's going to be like our synthesis or combination or decomposition reactions are examples of those, right? When you create a free element or join them. So same thing as single replacement, right? You have free elements in a single replacement reaction. So let's take a look at a few reactions. And the first thing we're going to do is, I think a great way to start off is practice identifying what type of chemical reaction do we have. So we have a compound plus another compound, making another compound and another compound. So this is a double replacement reaction. Double replacement reactions are not redox. All right, so that's one way I can go about this. Now I can also look at assigning oxidation states, and I should be able to tell that the oxidation states have not changed. So I go to my periodic table and I find that sodium is a +1. So chlorine is a -1 because the sum of these numbers has to equal 0. Going to my periodic table, potassium is a +1. Oxygen, -2. Hydrogen, +1. So then the sum of the oxidation states is 0. My oxidation states are correct. Sodium starts off as a +1, chlorine's a -1. Potassium starts as a +1, oxygen's a -2, hydrogen's a +1. Now let's go to, and let me just get my eraser so I can just erase those little C's down here. And let's now see what happens to sodium, oxygen, hydrogen, potassium, and chlorine on the other side of the reaction. So sodium, periodic table says +1, group 1, always +1. Oxygen is -2. This is not a peroxide where the oxygen is something other than -2. And hydrogen, most of the time, +1. Potassium, group number 1, is +1. So therefore, chlorine must be -1. So notice sodium starts and ends at +1. Chlorine starts and ends at -1. Potassium stays the same. Oxygen stays the same. Hydrogen stays the same. Then again, not redox. But I can also do that by identifying the type of reaction being double replacement. So now in our next example, I have magnesium plus hydrochloric acid makes magnesium chloride plus hydrogen. I have an element plus a compound making a new compound plus a new element. This is a single replacement reaction. Magnesium is an element by itself. It has an oxidation state of 0. Hydrogen has an oxidation state of +1, and chlorine is -1, right? So hydrogen being +1 from my periodic table, and my oxidation state rules of hydrogen most of the time being +1. Chlorine, therefore, will be -1. Magnesium combined in a compound with chlorine, I look at my periodic table, magnesium is a +2. This magnesium is not combined, it's an element, so it does not have an oxidation state of anything other than 0. No electrons lost or gained in an element by itself. So now this chlorine is -1 because 2 -1s balance off that +2. Plus, I look in the periodic table, I know magnesium is positive 2, so chlorine must be the -1 charge from chlorine on the periodic table. And now here I have a diatomic element by itself, so it has a charge of 0. So now that is picking the redox reaction. Is there a change in oxidation state? Yes. So this is a redox reaction. Magnesium goes from 0 to +2, and hydrogen goes from +1 to 0. And the chlorine stays the same. So magnesium and hydrogen undergo a change in oxidation state or oxidation number. So therefore, we have a redox reaction. So now we need to be able to figure out which elements have been oxidized and which elements are reduced. So remember, in oxidation, the oxidation number increases, right? And the name of our lion, Leo, lose electrons, oxidation. And in reduction, oops, let me just go over here. In reduction, our oxidation number will go down, and it goes down because gain electrons reduction. Leo the lion says, grr, big ox, oxidation number increases in oxidation. So now let's work on which species, right? Which is going to be means which element or compound, which part of a chemical reaction is oxidized, and whichever one has lost electrons, lose electrons, oxidation, and it's whichever has a higher oxidation number, and whichever one becomes more positive by losing a -1 charge. Now, which one is reduced? Whichever one gains electrons. Leo the lion says grr, right? And so oxidized, right? Whichever one has a bigger oxidation number is oxidized, big ox. Whichever one has gained electrons reduction, lower oxidation number, and becomes more negative. We're going to need to look to see what happens from the left side of the arrow to the right side of the arrow to oxidation states. So now let's go through and we're going to identify which is oxidized and which is reduced. So who lost and who gained electrons? First thing I have to do is I need to assign oxidation numbers. So step 1, we need to have our oxidation numbers. Now going back to my rules, sodium is an element by itself, so it has an oxidation state of 0. Going to my periodic table, hydrogen, most of the time, unless it's with a group 1 or group 2 metal, hydrogen is going to be +1. So if hydrogen's +1, then the chlorine charge we use is the -1 because that has to add up to 0. Now let's go over to the other side. Sodium here is now in a compound. So sodium's in group 1 of the periodic table. So in a compound, it loses 1 electron and makes a +1 charge. So then chlorine must be -1. And now here I have a diatomic element. So it has a neutral charge. No electrons lost, no electrons gained. So remember, elements by themselves have an oxidation state of 0. Elements in a compound where you need to determine the oxidation states using the periodic table and sometimes a little bit of math. So now let's see what happens from one side of the reaction to the other. Sodium goes from 0 to a +1. So then that sodium goes from 0 to a +1. So that means that the oxidation number increased. Remember, oxes are big, big ox. Lose electrons, oxidation. So that means that the sodium has lost electrons. Therefore, its oxidation state went up from 0 to +1. Now let's see, hydrogen goes from, let's see what happens. So hydrogen should be the one that reduced. So hydrogen goes from a +1 to a 0. So hydrogen goes from a +1 to a 0. So now +1 to 0 means that the oxidation number went down. That means it was reduced. That means it gained electrons reduction. So sodium is oxidized and hydrogen is reduced. And this is a single replacement reaction. So it is definitely oxidation reduction. And especially because I can now identify that sodium was oxidized and then the hydrogen is reduced. Now, nothing happened with the chlorine, started off and ended up both as -1. We're going to just kind of cross that out a little bit over here. So that means those are spectator ions. That means they just don't do anything. They don't change oxidation state. So now let's take a look at this next reaction. We have CH4, which is methane, combines with oxygen, producing carbon dioxide and water. When I identify my type of reactions, this is a combustion reaction. And from our earlier notes, combustion reactions are redox reactions. There's always a change in oxidation state because I have an element by itself. And then that element ends up in 2 different compounds. So I am going to definitely have a change in oxidation state. So now I need to assign my oxidation numbers. And I have to figure out what happened. So I want to go with the rules that I have from my previous slides. I didn't have a rule for carbon, but I did have a rule for hydrogen being +1, unless it's with a group 1 or group 2 metal. So in this case, hydrogen is a +1. I have 4 positive ones. So that means a total charge of +4 for the hydrogen. So that my carbon must balance that charge out and add up to 0 and be -4. Now I have 2 of these oxygens. They're both equal to 0. I'm ignoring that coefficient. Now let's go over here. I have carbon and oxygen. I'm going to go to my periodic table. I'm going to use oxygen's -2 charge. This is not a peroxide, so oxygen is -2. Use that periodic table charge of -2. Now I have 2 of those oxygens. Each one is a -2, so oxygen's total charge is -4. So now I have 1 carbon that has to cancel out a -4. So that means that this carbon is +4. Now let's go over to the water. I have hydrogen being a +1. I have 2 of those. So that means that I have a +2 charge for that hydrogen. And my oxygen is a -2. -2, +2 equals 0. All right, so assigned oxidation numbers. I have determined it's a combustion reaction, so it's a definite redox reaction. Now I just need to see which element lost electrons and gained electrons, which one is oxidized, which one is reduced. Remember, oxidized, I'm looking for the oxidation number to get bigger. Oxidation number goes up. And reduction, right, means small. Reducing means make smaller. So I'm looking for whichever oxidation number decreased from the left side of the arrow to the right side of the arrow, from reactants to products. So let's start over here. Let's see what happens to carbon. Carbon goes from -4 to +4. So if I go in a number line from a -4 to a +4, that's definitely getting bigger. So I'm going to say that the carbon is oxidized because it goes from a, oops, not a +4, it's going to be a minus. Let me erase that. Let me go back here to my pen. So I go from a -4 to a +4. So that's going to be oxidized. So that means it loses electrons, right? So that means it's going to be oxidized, right? Leo the lion says grr. Leo the lion says grr. Gain electrons reduction, lose electrons oxidation. So now which one was reduced? Which one shows a reduction in the oxidation state? Oxidation number goes down. Oxygen goes from a 0 to -2. So then my oxygen is reduced. The oxygen goes from 0 to -2. So that means the oxygen gains electrons. So that's how we identify which ones are oxidized and which ones are reduced. Now, let's just say, how many electrons do you think that carbon has lost or gained here? The electrons lost have to equal the electrons gained. So carbon goes from a -4 to a +4. That's going to be a lot of electrons. But let's take a look over here. I think I like the sodium going from 0 to +1, right? Loses 1 electron. And the hydrogen is going to gain. Each hydrogen is going to gain 1 electron. Notice that I do not have a balanced equation in the first one. All right, so now we're going to look at reducing and oxidizing agents. I like to think of these as secret agents, and the secret agent is going to flip their identity. So the reducing agent, right? So the secret agent, identity is reversed, is whichever one is oxidized. So we identify which one is oxidized. We call it the reducing agent. So the reducing agent is whatever it causes the oxidation. So it causes something to be reduced. That's why it's called the reducing agent. The thing that's oxidized causes something else to be reduced. And our oxidizing agent, secret agent, flip identity, is whichever one gets reduced, whichever one gains electrons. And it causes something else to be oxidized. So remember, these things happen simultaneously. The loss and gain of electrons happens at the same time. It's spontaneous, and the loss of electrons equals the gain of electrons. The reducing agent causes something to be oxidized. The oxidizing agent causes something to be reduced. All right, let's look and see. We want to identify which one's oxidized, which one's reduced. Remember, oxidized, big Ox, right? Oxidation number should be going up. And oxidation for reduction should go down. So I have to identify the oxidation states in the chemical reaction using my rules. An element all by itself, uncombined, oxidation state of 0. Element uncombined, oxidation state of 0. Going with my periodic table. Hydrogen is +1 because bromine is not in group 1 or group 2. So hydrogen is +1. That means the bromine is a -1. Now I'll go over to the other side over here. I have zinc and I have bromine. I go to my periodic table and I find zinc, and zinc is a +2. And so that means I have 2 -1s to balance that out. All right, so assign oxidation states is my first step. My second step, I want to see which one goes up from the reaction side to the product side, right, left to right, which one goes down in oxidation state from the reactant side to the product side. So zinc starts here. Let's see at 0. Where does zinc end up? Zinc goes from 0 to +2. So zinc has an increase in oxidation state. So our zinc is oxidized. And we have hydrogen goes from a +1 to a 0. So now that's decreasing. The oxidation number is going down. So our hydrogen is being reduced, right? These are the things that are being oxidized and reduced on the left-hand side. We have to look to the right, to the other side, however, to determine if it's oxidized or reduced. So this H2 over here is not oxidized or reduced, and neither is that zinc. It's over here, the reactants that are getting oxidized or reduced. So now the oxidizing agent is the one that gets reduced. The reducing agent is the one that was oxidized, right? Because the secret agents flip their identities. So which one was reduced? That was our hydrogen with the +1. So that's our oxidizing agent, causes the zinc to oxidize. So our reducing agent is the one that's oxidized, which is that neutral zinc, and it causes the reducing causes the oxidation. I get a little bit tongue-tied at the end of the day. All right, so that's how we identify the oxidizing agent and the reducing agent. So which is more important for you to know? Absolutely, you have to be able to assign oxidation numbers. You absolutely have to be able to ID which one has oxidized and which one has reduced. The oxidizing agent, reducing agent is not as big of a concept, most likely not heavily tested. So please focus on identifying which ones are being oxidized, which ones are being reduced, which one loses electrons, which one gains electrons. And then worry about the oxidation agent and reducing agent if you feel like you've mastered identifying oxidized and reduced. So let's go to zinc here. Zinc goes from 0 to +2, right? So that means it has lost 2 electrons. And let's say what happens to hydrogen over here, right? I've got a hydrogen that goes from a +1 to a 0. So now that's a difference of 1 electron. But now remember, I have 2 of those positive ones. So then here we do have a gain of 2 electrons. Okay. Which is then going to bring us to half reactions, which I'm going to do in our next set of videos, because in half reactions, you are going to have to determine, assign oxidation states, determine oxidized and reduced, as well as now taking it one step further and writing a half reaction. Actually, let's just continue with that and we'll just do this video and get it done with. So a half reaction is a reaction that shows only oxidation or only reduction, right? It's a half of a reaction. We're only showing one half at a time. That what happens in the overall. So our reduction is going to show the gain of electrons, and our oxidation is going to show where electrons. So reduction, I'm going to put electrons, and if it's going to be gained, electrons are going to be on the reactant side of the arrow, right? Reactant side is what side of the arrow? That's the left of the arrow. And our reduction, where we're going to show the loss or things get reduced on the product side of the arrow, which is the right side of the arrow. And we must follow the law of conservation of mass and charge, right? So I have to have the same number of each element on both sides. And my loss of electrons has to equal my gain of electrons. Now, ions that stand by and watch do not lose or gain electrons, and we do not write them in the half reaction. So we're going to have to start off by assigning oxidation states and determining if this is a redox reaction. This is a single replacement reaction. Single replacements are always redox. That means if something is oxidized, something is reduced, I need to figure out which one is which by assigning oxidation numbers and seeing which one happens on which side. So an element uncombined, oxidation state of 0. Element uncombined, oxidation state of 0. Using my periodic table, my hydrogen will be a +1. My chlorine will be a -1, right? Because my sum of my oxidation states has to equal 0. Using my periodic table, my zinc will be a +2. And my chlorine will be a -1 because those 2 of those -1s have to equal the +2. So then first step is assigning my oxidation numbers. Okay. Now I need to identify which one is oxidized, which one is reduced. Zinc goes from 0 to a +2. So since zinc goes from a 0 to a +2, the oxidation number increases, right? Big ox, that means this is going to be oxidized. So then my oxidation half reaction is going to start off with zinc, and it starts off as neutral. So I'm going to just show what happens to zinc from the left side to the right side. So zinc starts off at 0, and then I'm going to give a reaction, and zinc ends up as a +2. Now I have to show these electrons. Electrons I have to place by balancing the charge, which means I have to have the same numerical charge on both sides of the arrow. Doesn't necessarily, they don't cancel each other out across the arrow. I need the same numerical charge on either side. Remember, an electron is equal to -1. So I'm basically adding -1s to either the left side or the right side. So reduction and remember, oxidation is lose electrons. And I want to put my electrons on the product side. And that balances, right? If I start adding -1s, I'm going to end up reaching 0. 2 -1s plus the +2 equals 0. So then this shows oxidation. I have 1 zinc, and it makes a zinc +2 by losing 2 electrons, right? We put them on the product side. If I put the electrons over here on the reactant side, I would be adding -1 to 0, and then that would be getting lower in oxidation state, and I would never be able to reach this +2. Remember, it has to be equal on both sides, the charge, because the law of conservation, right? Matter, energy, and charge are equal from left to right. Now let's write the reduction. So first of all, let's see which one is reduced. Hydrogen goes from a +1 to a 0. Chlorines goes from -1 to -1. So chlorines are spectator. We don't include our spectators, right? They just watch. They're not playing. And our hydrogen, right? Our 2 hydrogens, right, are at a +1 charge. And then I'm going to draw my arrow. And now I end up with this hydrogen with a 0 charge. So now I have to figure out my electrons. Now, electrons have to balance the charge, so I get the same numerical charge on both sides. So I have a +2 on the left and a 0 on the right. I have to add my electrons over here. I'm going to add 2 -1 charges, because then that balances off the 2 positive ones. So then the reactant side equals 0 and the product side equals 0. And this shows our gain electrons, because in our reduction, the electrons are a reactant, right? Because I have to gain them or add them. And notice the loss of electrons equals the gain of electrons. And I still have my conservation of mass, 2 hydrogens to 2 hydrogens. And that is going to wrap up. We're going to practice a lot with oxidation and reduction half reactions. And if you need some help, go back, rewatch these videos, do some practice, connect with myself or Mrs. Mitiga, and see if you can get some extra help if you need it. It's going to take some practice, right? I will see you in our next video.